So, good afternoon. It's a pleasure to have here the Computer Laboratory of the University of Cambridge, Antonio Longa, who is a third-year PhD student at the University of Trento and has studied in Milano. And his talk is on neighborhood matching creates realistic surrogate temporal networks. Thank you.
Thank you for the introduction, Pietro. Let me share the screen. So I think now you can see this sharing. Okay. So I think we can start. So as Pietro told you, I'm Antonio Longa, third-year PhD student at the Fondazione Bruno Kessler and the University of Trento. And today I'm here to talk about temporal network generation. I'm going to start with a really brief introduction on networks and the temporal networks. And I will move on egocentric temporal neighborhood. And finally, we will go to temporal network generation. I think it's super clear for us what a network is, but basically it's a pair of sets of nodes and edges. So, and we also know really well that we can model social networks, moleculars, sentences, and even images. However, many times the real world, those structures are not enough to represent real world scenarios. Like we have the interaction change over time. So for instance, in like face-to-face interaction, we know that they change over time because we maybe start talking with someone else, or images could be videos and traffic on roads and this kind of stuff. So temporal network solves this problem. And how can we represent a temporal network? Well, we can have an ordered sequence of static graphs. Suppose that we have this graph here, it's simple graph that is temporal. Then we have label on edges that tells you which time the interaction is happening. So for instance, the edge between A and C happened at time step 3, okay? And so we can model these as a sequence of static graphs. Cool. Now, let me introduce you to the egocentric temporal neighborhood, for short ETN, in which suppose that we have our our sequence of ordered static networks. And what we can do, we can, of course, map each node to different layer. Here, one layer represents one temporal step. Suppose that we choose k equal to 2. So we have 3 layers in this case, with k equal to 2. We choose for an ego node. And what we do, we take the first order neighborhood of the ego node at each time step. And what we have is this structure that basically it's like, let me say that it's a 3D structure in a sense that we have layers and our layer evolves and we create an edge among the same node, like here, because A is still A, but it just changed time. And then we have the connection with the node. Okay, what we can do with this structure? First of all, we can build a string that allow us to basically go from the string to the structure and from the structure to the string. And how it works with this encoding, it's super easy in a sense that first of all, we have a node encoding for each node except for the ego. So the node representation as the node embedding has a length equal to the number of layers we're using. So in this case, we are using 3 layers and the embedding will be of 3 bits. And what we do, we put a 1 if and only if the node is connected at the ego at that time step. So for instance, the node A is connected to the ego at time step 0. And in fact, that in position 0, we have a 1. That is not true for the node B because it's not connected at time 0. Cool. When we have this node encoding, we simply sort it and we concatenate it. When we have this string in a paper, we show that in the paper, we show that there is that comparing strings is identical to do the isomorphism test. And in fact, the complexity of this algorithm is really low compared to the real isomorphic test. And this is an exact algorithm. Of course, it is working only for the first order neighborhood. Otherwise, this trick is not going to work. But now we have an algorithm to compute if two egocentric temporal neighborhoods are identical, and we can do it in a really fast way because we have just to compute if two strings matches. Okay. Go. Yes, sir. In this case, for this example, they are not. But if they will be attributed, suppose that since we are talking about social interaction, we know that the A is a patient, while B is a doctor. What you can do, you can, instead of using a bit for each time step, you can use something bigger, like the encoding of the doctor. You see what I mean? Instead of having in this case, we have, and in this case, we can easily insert even other informations. In this work, an efficient procedure for mining egocentric temporal motifs, we show this fact that I already told you, that the fact that identical structure are captured by the same signature. And also we show, only using a simple, only using the distribution of those ATN, you can get the similarities among different social, among different temporal networks. And what is cool here is that if you have a look to high schools, they are quite similar among them, and also the office and the hospital. And in the meantime, if you have a look, the university stay in the middle of among the hospital and the workplaces and the high school. But this is another work, let me say. So, okay, what can we do with those ATN? We can generate a temporal network. And here is the main part of the talk. Here is just to recap you that we extract these temporal snapshots, we extract ATN, and we compute a string that represents this structure. What we do? Well, we build what we call growth dictionary. So basically, each we are starting from the ATN in panel B in the left. And what we do, we remove the last layer. So I have this X, red X, to show you that I'm removing the last layer. And indeed, the key, the signature, is just cut the last number of each node encoding. So for instance, we have 0111111 that becomes 01X11Y. And we can use this as a key of a dictionary. And as a value, what we have all possible extension of one-step extension with their probabilities. Because since we are counting them in the original graph, then we can just count these probabilities. And then, for instance, this key 01X11Y goes into, I don't know, 010110 with a probability of 0.35. Because we know it, because we mined it in the original graph. Once we have this dictionary, what we can do, we can start from a seed graph. So basically, two snapshots. What we do, we take a node, one node, we use it as a ego node, we extract the ATN, we query the dictionary, and we pick one of the values according to their probabilities. Perfect. Now we have the, let me say, the new layer, and we attach this new interaction in the new layer. Okay. Sure. But the probability comes in this part, in dictionary building. So it basically counts how many times that specific motifs, that specific neighborhood appears. Yes, in this step here, in which I'm building this dictionary. And when I have it, I already have the probability that having that key, I will get it on that structure or on that structure.
So, for example, in the bounded dictionary part, so the top left one has 0.35 probability, and the next one has 0.2.
Exactly.
But in the previous step, that connection already. So when that step has the over probability.
What do you mean? No, I mean, the probability is related to the last part of the motifs, because the first part is the key. So basically what we have the key, that is just this first part, and here we have all possible combinations that we found in the original graph.
I feel that the point is that we do expect that given sort of similar connections that have a high probability.
I mean, this one is just an example. I mean, it's not because it's huge, and here it's just an example. So, but for instance, in this case, maybe the fact that the probability that the interaction are shorter, because you already have an interaction of 2 times step, and maybe there is the high probability that it ends. Okay, once you have the dictionary. No, we use, I mean, it's a parameter, and in the result I'm going to show you, we use 2 temporal steps. I mean, key equal to 2, meaning 3 temporal steps. And okay, so we extract this structure, query the dictionary, get this new structure, and we use the last layer to build what we call provisional layer. You can see from the image that in the provisional layer we have, first of all, it's directed, and moreover, there is the question mark, because there could be the possibility that there is a new node, and we don't know yet which of the other node is. Okay. And what we do, we repeat this procedure for each possible node. So we consider each node as an ego at least once. Once we did this, what we have? We end up with this provisional layer, and we want to validate connection of this layer. And what we do? First of all, we confirm all the bidirectional edges. Then what we do, we randomly validate half of the other edges. And the reason why we are using only half of them is because when you are considering the ego, and since you are considering all possible nodes as an ego, each edge has been seen twice. And here is why we remove it. Once we do it, there is the last part in which we have these stubs, and we randomly connect stub among them. Okay, this is the procedure, the general idea. And in order to show the results, I have 3 competitors. I present 3 competitors. 2 of them, STM and Diamond, are based on temporal motifs distribution, while TagGen is based on deep learning. It basically uses random walk, temporal random walk to generate a network. Have a look to the results. Here I'm showing 3 different data sets, an hospital, a workplace, and an high school. And the plot show the number of interactions with respect to the time. You can see that here we have the number of interactions, and here we have the time step. It's really easy to see that this one is day, night, day, night, day, night, day, night, and so on and so forth. And for instance, above we have the weekend in the middle. Okay, the original network is the black one, while the one that we generate is the orange one, and then we have the blues that are competitors. You can see that okay, another point, we have two plots in the same line. One, like the small plot is just a zoom out. And the reason is, you can see that STM and diamond that are in the main plot, they do not capture the periodicity, the day-night periodicity, and neither the week-weekend periodicity. And they try to stay in the middle, while CapGen is able to capture the day-night periodicity, but in a totally wrong magnitude. Because, for instance, here we have up to 60 number of interactions in a specific time, but CapGen generates something like 400 number of interaction for that time step. And then in the right, we have the number of nodes, because some algorithms keep adding nodes to achieve certain properties. So for instance, STM, that is the second bar, has really a lot of nodes more with respect to the original graph. So another point to evaluate the similarity is based on the distribution of the of some metrics. For instance, here we have the number of interaction. Again, one for each of the three datasets I'm using. The first one is the original, the violin plot of the distribution of the number of interaction. Again, Gen is our algorithm, and then we have competitors. And this is just a visualization of the similarity. So it's just visualization. We have the new conversation we have. So suppose that we are talking with each other, and then a new person join us. So it's a new conversation. And also we have the duration of contacts. So how long my conversation works, for how long, and the average shortest path, and we have several metrics in the paper. In the end, what I would like to say is the scalability of the method, because here I'm showing that we are running this algorithm with 10 datasets, different datasets. And one question may be, and where the competitors are? Well, here is the key point. In terms of time, our algorithm is extremely fast compared to the competitors, because we, for instance, in the hospital, 70 seconds, while Diamond, STM, and CapGen are much more slower than our algorithm. And the key point of this work is that now we have a mechanism to extend in both time and number of nodes an input graph. In order to test this phase, what we do, we took a dataset, in this case, workplace. We have 2 weeks. What we do, we took only 1 week. We build our dictionary on this, let me say, training phase, and we compare the entire graph generated with the original one. In the same manner, we did for the sites expansion. So we took the high school dataset, we took half of the nodes, and so having this as a training. And what we do, we generate, but increasing the number of nodes, because for us it's just a parameter, is a parameter of the graph, the seed graph. And still we are able to achieve the same periodicity. And yeah, this is the general idea. So in which we generate a temporal network. And yeah, that's all. Thank you. Do you have any questions? Are there questions? Yeah.
I'm curious, where does the memory come into this algorithm? If you mentioned at some point that you bring access to create the next one, but I don't know what the number of times, but I'm assuming that they keep there are more than times.
Yeah, there are. Okay. Well, there are two key points here. Well, the number of snapshots are really too much. Like, for instance, we have 1,200 for the hospital time steps. And in fact, the decision of the number, the K, so how many time steps taken in consideration, is an important interparameter of the methods. And what we think is that all this kind of information is within the probability in the dictionaries, because you have this local probabilistic model, this dictionary, and depending on the input structure, probably it brings to having this kind of periodicity.
So in the hospital and the workplace,
yeah, 3 K is equal to 3 for all the data sets. The only difference rely on the aggregation we do, because all these data set, no, joking, all the first 6 data set came from social pattern, that is a association in which they used physical devices, and every 20 seconds the device record the interaction, okay? While, for instance, SMS and calls, just SMS and calls. But due to the different nature of the type of communication, we used an aggregation of, if I remember correctly, of 2 minutes for the face-to-face interaction and 5 minutes for the SMS. But this, because if you consider this block, you have an average of one interaction, so it's really, really small. So I think we can even increase it a little bit. But
it's still a bit clear to me, because so if I'm understanding you, say the time steps, you get that code, you will be predicting that it sounds or not on the code. But the sound is running, so often it moves 2 steps.
yeah, it's. I think that yeah, I think that I mean, those dictionaries are really big, and I think the key value is inside those dictionaries. We are still trying to explore them, and what we think it can be interesting is to combine them. What I'm trying to say is that suppose that you have a primary school and a high school, and you would like to combine them. Then you have the dictionary that contains all the information, and then you can work on the dictionary and generate a network that maybe is in between 2. Yeah?
So that is one for
yes.
So it's each, let's say, this step forward from the prediction.
What do you mean, sorry?
So for example, if you move it, step 200, 201.
Yes.
202.
Yes.
And that's how we evolve.
Yes. Yes. Basically, is this part here, in which I'm starting from the graph seed, is then repeated with the generated layer and the second last. And so you have this like sliding window moving, and then you use it. Not with the prediction. Yeah, with the prediction. And yeah. Are there other questions? Yes. I mean, yes, but well,
over time are the same. So in the high school, you have
yes.
They're just like common edges.
Well, actually, in this kind of plot, because I think they are nice to see, I'm showing only the number of interaction and the time. While in the paper, we have a lot of metrics. because one of the biggest problems in temporal graphs is how to evaluate the similarity. So what we did is, first of all, we have these 10 different metrics in which we have the density, the clustering coefficient, the assortativity, really a lot of them. We have the distribution, and then we use the KS Kolmogorov-Smirnov distance to measure the similarity among those distributions, okay, to the real network, yes. And here, a smaller value is better. And we have this kind of comparison in both topology of the network, but then we also have the dynamic because, for instance, we simulate a random walk, not one, many random walk, and we evaluate the coverage and the mean first passage time, or we simulate a SEER model and then we evaluate the R0 distribution in order to have, let me say, much more stronger comparison in terms of dynamics. Like for instance, here I'm showing that, take for instance the hospital, I'm simulating a SEER model. I have the lambda of the model because the epsilon was fixed. And you can see the black horizontal line that is the stability of the simulation in the SEER model, in the original graph, so that you have like a baseline, and then we have our result with our standard deviation. And there are even cases in which, okay, if you take the high school and you take our result, it's even less, it's smaller than the standard deviation, than the stability of the original one. So evaluating the similarity in terms of dynamics is not easy, an easy task.
In this case, you talk about this signature.
Mm-hmm.
How that might accommodate increasing the
well, yeah. Okay. Suppose that you have this graph and this representation. Okay. You have the node encoding, and suppose that a new node arrives, a node C, and is connected to the ego. What you have to do, you have just to compute the embedding of the node C. So assuming that the node C arrives in the last time step, then what you have to do, you have simply to add 001, because you know that previously the node wasn't attached, and now that it's attached, the only problem is that you have to put the node encoding in the right position when you are sorting. And so it's just this one. Maybe from the basically, it's not really an isomorphism test. It's just that you are considering only the first order neighborhood. This is why you can build a signature that contains all the information of the graph. If you would like to move to second order, it's not going to work. And this is why our algorithm is super fast in terms of mining and also in terms of generation. No, it's the baseline. I mean, I started with this work here, and well, I was like looking into graphlet, and I was drawing this graphlet and the reasoning, and I thought that those graphlets are indeed temporal graphs. If you took a graphlet and you turn it, you can see at time steps. And then from that point that we started, and then the intuition just, I don't know, I don't remember, but came up in some way. After age of crime. So I think we have a question from Dobrik. Okay, Dobrik is asking for how do you deal with permutation invariants when querying? For instance, querying 01x, 11y should be the same as 11y, 01x. In order to avoid this problem, we sort it. And this is why we have to sort. In the slide I'm sharing, we sort the node encoding. And even if it's weird, but we sort using the encoding, let's say, integer value, okay? We sort it, and we have this sorting, we don't have this problem of ordering invariant, because in some sense, we are imposing an order. I hope I answered it to you. I think yes. Okay, I think if there are no other questions, I think we can close.
So what will be your future stance for this?
Well, first of all, there is nothing related to differentiable part. So it's just a matter of mining and use it. And an idea could be used, could be the one to use those structures even in GNN, one idea. Other ideas came from the higher order structure. What if instead of having ego nodes, we still have ego nodes, but connected to higher order structure? Because we think that especially for face-to-face interaction, we have higher order interaction. And an idea to use those higher order interaction to do this. Another idea rely on the fact that this work lose in the long-term memory. What does it mean? It means that, okay, if I'm talking with you because we are friends, then tomorrow, due to my ego structure, I will have the same probability to talk in the same manner I talked with you, like duration, many people, and so on and so forth. But it's difficult to capture that I'm talking with you because you are my friend and not a random person. In order to capture this long-term memory is not captured by this method, and there is the idea to even capture this like long-term memory. And since there is the easy extension to replace 0, 1 with something more like basically insert the information of the node, we are also thinking to generate like, okay, generate an hospital with 10 doctors, 100 patients, 30 nursery, and you can specify how many figures you want. And it's an easy extension to this because it's just replacing 0, 1 with the encoding of the figure.
Do you get data from hospitals?
We are using social pattern that they collected this face-to-face interaction in an hospital, and they are public available on this website, on their website. This is a key point. Well, this work started at the beginning of COVID because we did this work on basically COVID started and people started saying, okay, we can use tracing app, like digital contact tracing. It's the right direction, cool. But then many questions arises. Like Bluetooth, first of all, Bluetooth is not the technology for capturing distances because there are a bunch of paper that show you that it's not easy at all. identifying distances. And moreover, there are many problems because children do not have smartphones. And one question was how many people have to have the app in order to make this contact trace, this contact works. We did this work with this simulation on DTU. It's a data set of face-to-face interaction using the Bluetooth from Copenhagen. And it's something like 3-year data set. But still, it was small, this kind of simulation, because it was only 700 persons. And when we did this work, one reviewer asked us, okay, but how can we extend this, make it bigger? And this is, I think it's a huge application. So for simulation in a real scenario, you now have an algorithm to generate bigger data sets. So let me say data augmentation to simulate. And moreover, another application we are thinking is that since you are generating a similar network, maybe this work can be used for privacy preserving. Because instead of giving you the data set, I will give you dictionaries. And then you can generate the data set. But it's generated data set, it's not the original. So the privacy of the users is covered because I'm not giving you the data, I'm giving you those dictionaries. And we are trying to test if it's true that you cannot break the privacy of the people with this kind of stuff. And these are some ideas of possible